Hi. So we'll talk about the recommender systems ranking structure, and we're doing that so that we can lead up to a story, an idea, a, a proposition towards how to change recommender systems in the world of LLMs and how to learn from LLMs. But first, in this first video, we will try to understand what are the internals of a ranking model of recommender systems, and at a very high level, recommender systems, the cascaded pipeline that is used in most recommender systems is there's a retrieval layer which produces a small set of candidates, small relative to the corpus. Typically, the set of recommendable videos or content or friends or whichever music, whichever domain you are talking about, is millions, potentially billions, and that's a very large number to rank all the time. So there's a retrieval layer, which brings it down to a thousand candidates or so. And then, and this is the part we are going to talk about today, the ranking model. The ranking model then takes these candidates and tries to produce high accuracy estimates of the user actions that would take place if these candidates are presented to the user. And once you have these estimates, you have what I'm calling as a value model, which combines them into a single score. So let's go over this a little more detail. So what we said is that we have a manageable, I'm not going to say word like small, but like maybe within your capacity budget, a manageable number of candidates. For each of them, you are producing probabilities of the observable user actions. These need to be observable because you will then use the observed values, like you will use your ranking model and you will present candidates to the user, and the user will take some actions, and you will go back and make this training data to improve your ranking model, right? So that's why these are observable actions, and your ranking model is actually an estimator model. It is not really ranking. This model comes up with probability estimates for each of these user actions. Okay, so the two parts of the ranking setup, one is this estimator model, and the second is this value model. The value model then typically is a linear combination. These weights are some things that you can experiment and fine tune and figure out what is the best for your business. But so once you have these estimates, you take a weighted combination of them into a combined value. So at this point, you have a single score. Now, obviously, linear weighting is not the only way. There can be others, and we can talk about what is suboptimality, if any. But suffice to say, this is separate from this estimator model. So what we are going to talk about primarily is the estimator model, and later on we'll see the structure of it. So that's why I want to help you understand the API, or the expected output of this estimator model. Okay, so what we have here is the estimator model is producing um, these probability estimates of the actions, and then another inference reward model, to borrow the language of LLMs. An inference reward model, which we will hereafter call value model, is combining the outputs of this estimator into a value or a score that can be used to actually decide which items to show to the user, which candidates to show to the user. Okay. Um, so let's go into this ranking model. Again, I'm going to continue to call it a ranking model, although it is really not ranking. It is really an estimator model, but that's the nomenclature you're more likely to encounter if you go to an industrial recommender systems team. So the ranking model has user history. These are the input feature types: user history sequences, float features, embedding features, and sparse features. Now, what do they mean? Explain a little bit here. So float features are typically single values. Like in friend recommendations, they could be the number of mutual friends between the viewer and the target, the person being recommended. Or they could be things, they're still floating points, but things like cosine similarity between embeddings of the viewer and the target. So there's at some layer there are embeddings in this particular float feature. There's some layer there are embeddings, but they are already processed, and the actual feature that you have is a single value. That's what I'm trying to say. Float features are just single values. They need not be just float. They can be integers also. I don't know, the number of days the user has come to the app in the last 7 days. That's fine. So it's not really, float is not the term. It basically means to focus on. It basically means a single value. Okay. And the reason we are separating float features, and then we'll talk about embedding features and sparse features and user history sequence. The reason we are separating them is because they are processed differently. So float features are going through this, what I'm calling a dense arc. Embedding features are processed differently. Sparse features are processed differently, and that's why you're making the minimum number of groups you need for efficient processing. And this float features is a group of all single value features. Embedding features are not single value. They're like a set that comes. So, for instance, suppose you suppose you're doing video recommendation, and you process your video through an external LLM, and the LLM gives you a full embedding. Let's say 512 dimension embedding. So that set of 512 floating points is together something. So that's the embedding, and you want to treat it together, because then you'll just have much more model accuracy if you don't treat them as 512 independent float features. You could, but it's just it doesn't work out as well, because the embeddings, when they were trained, there was a structure inside these floating points that if you retain it in how you process it in the model, your model will be better. So I write some examples here, like the 128 floating points of 128 dimension graph neural embedding that you might have trained for your domain. Just the same thing, that the reason they are not treated as float features, because processing them in the model as a tensor or a vector leads to better model accuracy. Then you have sparse features. Generally, the last few years I think most of the advances on ranking model can be characterized as increasing the importance of sparse features, the contribution of the sparse features. Like 2-3 years ago, float features would be accounting for 99% of the model accuracy. And some of the best models out there today probably have even as high as 50 to 60% of the model accuracy is coming from sparse features. And it's a little bit the debate between feature engineering and letting your model figure out what features there are. That's sort of the debate that's playing out here. Float features are typically engineered features. You do a lot of work externally, and you have pipelines, a lot of human intuition that goes into exactly the feature. But sparse features and then user history sequences, these are about the model figuring out from the raw data. But not to get ahead ourselves, sparse features can either be class-based features like category ID of a song in music recommendation, or also lists of IDs, okay, like last n users IDs messaged by the user in friend recommendation. The difference between And you will see exactly the same thing in user history sequences as well. Last and user ID is messaged by the user. So the main difference between sparse features and user history sequences is that the user history sequences are processed by an attention model, which requires and relies on all of them, that the list that you have being preserved and being made available to the attention model. But in sparse features, even though input might have been a list, what you do is you just sum it up or take an average of it, and you forget that list. You just take one value for the entire list. So you can't use it in an attention model, right? It just becomes one embedding. So the output of a sparse feature is really an embedding, just like the output of an embedding feature is. The only difference is the embedding feature is the embedding itself. So you have trained it outside and you're just directly getting an embedding. The sparse feature are like IDs. They're class values that you map inside your model through an embedding table. And that's how you get the embedding. And just being able to train it inside the model provides a step change in accuracy. This co-trained embeddings has been transformational. Because you are learning what that category or what that user ID or what that item ID, what that means in your domain, in the context of your ranking model. Okay, so single values, collection of values that should be treated as an embedding but trained externally, and sparse and user history sequences. Sparse can be simple, like categories like, oh, the country of the user or the language of the user, or they can also be lists like last 10 videos watched by the user, etc. But the difference between, when you talk about lists, the difference between sparse features and user history sequences is that the processing of user history sequences retains the list, whereas sparse features just sums it up. Now you have a sequence here and it's going through attention, but everything else is like what is called the static pathway. And I'm borrowing this term from OneRec technical report. It's a very regarded paper right now, a very popular paper right now. They use this term, user static pathway, to refer to everything that is not a sequence feature. And to arrive at this pathway, we process it through what is called an interaction arc. This interaction arc is getting the float features and embedding features and sparse features, and then sort of finding combinations of each, or multiplications, or bitwise attention, whichever model architecture you use. I'll give you a specific example. Let's say you think, not you think, but let's say in your domain, good friend recommendations. Suppose you're working on friend recommendations. That's something I work on, this top mind for me. So let's say a good friend recommendation is one which has a lot of mutual friends, but also is in the same location. Okay, so this but also, or basically this intersection or multiplication operation, you can learn that through your interaction arc, because you have your float feature mutual friend count, and you have your embedding features, or the viewer and targets location embeddings. Perhaps you have their sparse feature, which is the zip code, or some sort of maybe country, language, something, ID. So you have components of your intended feature coming through different routes, and then this interaction arc learns to try these things out and then see what works, and then through gradient amplify what is working. This is what neural networks do, right? They take the inputs through different weights, they combine differently, and whichever thing works, they amplify the gradient, and then that's how they learn these features. So interaction arc is a way to learn better features than the inputs were. One total, like if you have training a model, one ablation you could do is your output of your interaction arc could be just a concatenation of the inputs. Is my interaction arc any good? You could ask that, right? Because okay, but let's actually keep going ahead and see what happens after that. So after that, you have the processed sequence features, and the processed user static pathway. These are also some dimensional embedding, if you will, of all these features, and then you concatenate them, and then you pass them through task prediction arc. I'm using MMOE, which is from this Watch Next paper. Watch Next Google paper. Recommending what to watch next. It's a fairly common architecture, but I wanted to show you the original paper in case it helps. So multi-gate mixture of expert model, MMOE, and broadly what it talks about is how to share some experts and how and allow tasks to determine which experts are better for them, things like that. So coming back, after you have processed your features, you concatenate them and you process them through some sort of task prediction architecture, which comes up with these estimates. Okay, that's about it. So broadly, what we talked about is your retrieval gets you some candidates. Ranking, which is an estimator model, produces estimates of for user actions, and your value model combines them. And the process of finding these estimates is through different types of features, which are groups which are based on how they are processed. And then we try to learn better feature interactions, and we use attention for the sequence features, combine them, pass them through a task prediction architecture. Thank you.